Welcome to Mrs. Lee's Chemistry Academy. Today we're going to cover atomic structure and periodicity, mainly focusing on atomic radius and ionization energy. Relating this to the learning objectives from College Board, that the student is able to explain the distribution of electrons in an atom or ion. The student can analyze data relating to electron energies and describe the electronic structure of the atom using PES data, ionization energy data, and or Coulombs Law. Predict and justify trends in atomic properties based on location on the periodic table, and also apply periodic properties to predict chemical reactivity. In terms of periodic trends, it can be explained by using Coulombs Law, the shell model, effective nuclear charge, and electron shielding effects. The three trends that we're going to cover will be atomic radius, ionization energy, and electron affinity. The Coulombs Law states that the force of attraction between two charged particles is directly proportional to the magnitude of each of the two charges, namely Q1 and Q2, but inversely proportional to the square of the distance r between them. And this is the formula. Now, if the two charges are of opposite signs, meaning like the protons and electrons, the force between them will be attractive. If the two charges are of the same sign, like electrons for core electron and valence electrons, the force between them will be repulsive. Effective nuclear charge is the net attractive force felt by a valence electron, as if there's a single positive charge located at the nucleus screened by the core electrons. It's represented as Z effective equal to Z minus S, where Z is the number of protons in the nucleus and S is the number of core electrons. Now, how does that work? Let's look at a lithium atom, which has the electron configuration of 1s2, 2s1. So the effective nuclear charge is equal to 3 protons minus 2 core electrons, resulting in +1. Effective nuclear charge increases when going from left to right across the periodic table because there's increasing number of protons. Another reason is the electron shielding effect. The core electrons are closer to the nucleus than the valence electrons. So valence electrons will experience repulsive forces when they are shielded from the full electrostatic attraction of the nucleus by the core electrons. Electron shielding effect increases down a family group because now there are more energy shells, more core electrons, and the outermost electrons do not shield one another from nuclear charge. Let's look at trend number 1, atomic radius, which is to half the distance between two nuclei of two covalently bonded atoms in picometer, which is 10 to the negative 12 meter, or between two metal atoms in solid crystals. The trend across the period is atomic radius actually decreases because there's more protons as one goes across the period. There's increasing effective nuclear charge experienced by the valence electrons. Therefore, there's stronger attraction between the outermost electron and the nucleus, resulting in smaller atomic radius. The trend down a family group, now it gets bigger and bigger for the atom because there are more energy shells, meaning there are more core electrons, increasing this electron shielding effect and reducing the attraction between the valence electron and the nucleus, resulting in larger atomic radius. I would like you to have a mental image of this diagram, not to memorize it, but remember when we go across a period, the atomic radius is getting smaller and smaller, whereas when we go down a family group, the atomic radius is getting bigger and bigger. Practice problem number 1. Arrange the following atoms in order by increasing size. They are bromine, cesium, fluorine, and calcium. Now, they are arranged in such order where fluorine is smaller than bromine, which is smaller than calcium, which is smaller than cesium. And the reasons are very obvious. Fluorine has only 2 energy shells, therefore it has the least electron shielding effect, making it smallest. Cesium atom has 6 energy shells. There's more core electrons, having the most electron shielding effect, making it the biggest atom. Now with bromine and calcium, they both have the same energy level, which is N is 4. Therefore, bromine is smaller than calcium because it has a bigger effective nuclear charge. Ionic radius is the distance between ions in ionic compounds. The cations are smaller than the parent atoms. For example, sodium is bigger than sodium ion. As we look at the electron configuration of sodium, it is neon 3s1, and sodium plus 1 ion is neon 3s0. And you can see that complete third energy shell is removed when sodium forms a plus 1 ion by losing the valence electron. Therefore, this sodium ion is smaller than the parent atom. Now when we look at anion, where the atom gains an electron such as chlorine and chloride, chloride ion is actually bigger than chlorine atom. Looking at the electron configuration, chlorine is neon 3s2 3p5, where chloride ion is neon 3s2 3p6. And now you know there's additional electron in the chloride ion, creating greater repulsion, making the chloride ion bigger than the chlorine atom. Isoelectronic series refers to ions that contain same number of electrons. If we look at the neon and look at those few atoms before and after neon, we come up with oxide minus 2 ion, fluoride minus 1 ion, and sodium plus 1 ion, magnesium 2 plus ion, and aluminum 3 plus ion. Now I always like to ask my students to rank them next to each other in terms of protons and electrons. As you can see, there are more protons in aluminum 3 plus ion and least number of protons for oxide minus 2 ion, although they have the same number of electrons. Now, as the number of protons increases, there's greater attraction between the proton and the electrons, making the ion to be the smallest. Therefore, one can rank the size as O2 minus ion bigger than fluoride, bigger than sodium plus 1, bigger than magnesium 2 plus ion, and bigger than aluminum 3 plus ion. It's all because of increasing number of protons, which reduces the size of the ion. Trend number 2, we're going to examine ionization energy. It is the energy required to remove an electron from an atom or ion in the gaseous state, and this energy is endothermic, positive in value. It is the minimum energy to remove the first electron, defined as first ionization energy. Now when we write the equation, we start out with sodium, which is already in gaseous form, and supply energy 496 kilojoule per mole, and it would knock off an electron to form sodium plus 1 ion, also in the gaseous state. The trend across the period is that ionization energy is increasing because the electron in the outermost energy level experiences a greater effective nuclear charge and is attracted more tightly by the nucleus, therefore requiring greater ionization energy for the removal. The trend down a family group. The ionization energy is decreasing because electrons in the outermost energy shell is further away from the nucleus and held less tightly. Therefore, it's relatively easy to remove the electron. And because of that, there's an increased reactivity down the alkali metal in group 1A because of the relative ease in removing the electron. As we examine both the atomic radius and ionization energy related to Coulombs Law, when we compare two species with the same arrangement of electrons that's across a period, the greater the effective nuclear charge, the smaller the atomic radius, and the higher the ionization energy. When we compare two species with different energy shells, the further the electron is away from the nucleus, the larger is the atomic radius, and therefore the lower the ionization energy. Notice that the two trends are in opposite direction. As atomic radius decreases, ionization energy increases. Here, I'd like you to have a mental image of the diagram of first ionization energy, and this is for from hydrogen all the way to xenon. As you can see, we start at a valley where you have the alkali metals, group 1A, and when we go across the period, it actually goes uphill to the peak. So with lithium going up to neon, and sodium going up to argon, potassium going up to krypton, and rubidium going up to xenon, ionization energy increases. However, if you look down in family group, you can see that there's a negative downhill slope. If you look at lithium, sodium, potassium, and rubidium, it seems that the ionization energy is going lower and lower. There are exceptions to the ionization energy trend. If you look at your periodic table in front of you, you notice that the boron lies to the right of beryllium in the periodic table, yet boron has a lower ionization energy than beryllium. We may ask ourselves why, and if you look at the electron configuration, you will know why. Look at beryllium. It has 1s2, 2s2, fully filled 2s orbitals, whereas boron has 1s2, 2s2, and 2p1. And it's going from the s fully filled orbital to the new electron in the 2p1 that creates the extra repulsion and therefore lower ionization energy for boron. For beryllium, the 2s2 is very stable, requiring higher ionization energy. Now, if you look at oxygen, another exception to the trend, which lies to the right side of nitrogen in the periodic table, but oxygen has a lower ionization energy than nitrogen. If you look at the electron configuration and the orbital diagram, we notice that nitrogen has a 2p3 half-filled 2p orbitals, whereas oxygen would have 2p4. Now this extra, the fourth electron in the 2p orbital, creates greater repulsion in the oxygen atom, making it easier to remove the electron and therefore lower ionization energy, whereas the 2p3 with half-filled orbital is more stable. Here's a diagram, a chart of successive ionization energy in kilojoule per mole for period 3. Now, if you look at sodium, you'll notice that first ionization energy is 496 kilojoule per mole, but when we go into second ionization energy, it's increased by roughly 10 times. And look at magnesium again. Second ionization energy is about 2 times of first, but when you go into third ionization energy, that's increased by 5 times when compared to second ionization energy. And similarly for aluminum, when we move from third to fourth ionization energy, is increased roughly by 4 to 5 times. Now, why such a big jump? This is because we are now moving from a valence electron to a core electron, and therefore a big jump in energy. And one can make use of this big jump to identify and predict the element or the atom, the family group of that. If we don't know it, we can predict it by looking at the big jump in ionization energy. Here's a recap of what I said earlier. As valence electrons are loosely held by the nucleus, they require less energy to remove when compared with the core electrons. Whenever there's a big jump in the magnitude of successive ionization energy, it means the energy used to remove a core electron from an ion with a noble gas configuration. The trend can be used to predict the number of valence electrons in an atom and its family group. Now let's continue with predicting family group. If you look at magnesium, the first ionization energy is 738 kilojoule per mole, and second ionization energy is 1450 kilojoule, whereas the third ionization energy is 7,730 kilojoules. Magnesium has an electron configuration of 1s2, 2s2, 2p6, and 3s2. Since it has 2 valence electrons in the third energy level, the second ionization energy is roughly 2 times that of the first, because now there are 12 protons holding onto the Mg plus 1 ion and making it holding more tightly after the first valence electron is removed. However, the third ionization energy is about 5 times increased, because now we are moving away from the valence electron. Now we're entering that of the core electron, and it certainly takes greater energy to remove because it resembles the noble gas configuration of neon. Second problem, why is the first ionization energy of potassium lower than that of calcium, but the second ionization energy of potassium is higher than that of calcium? Let's take a look at the electron configuration. Potassium ends with 4s1 valence electron, and calcium ends up with 4s2 valence electron. Now, calcium has more protons and therefore greater effective nuclear charge than potassium. And the greater effective nuclear charge in calcium would attract the valence electron more tightly to the nucleus than potassium. Therefore, first ionization energy of potassium is lower than that of calcium. Now, when we talk about second ionization energy, we're talking about removing the second valence electron from calcium plus 1 ion, but we are also talking about removing a core electron from the K plus 1 ion. And certainly, removing core electron requires more energy. Therefore, the second ionization energy of potassium would be greater than that of calcium. Practice problem number 3. We are looking at 3 unknown elements. They all belong to period 3. And let's examine their ionization energy closely and answer the following question. Which is the most non-metallic element? Explain. As you can see, when you look at all 3 of them, seems like element 3 would have the highest first ionization energy. Therefore, probably that is lying more to the right-hand side of the periodic table, and therefore is probably most non-metallic in nature. Identify element 2. Look at element 2. It has a big jump between second and third ionization energy, so probably this is magnesium with 2 valence electrons. Explain why the atom of element 2 has a larger radius than the ion. Remember, metallic atom, they tend to lose electron to become metallic ion. After losing the electron, then the remaining electrons are held more closely to the nucleus, making the cation to be smaller than the parent atom. What is the equation for the ionization of element 2 and the oxidation state of element 3, and rank the element by increasing order of atomic radii, and which one is attracted to the magnetic field? Now, these will be answered in the next slide. So a recap of point 1 and point 2, I have already talked about that. And point 3 also. Now let's go into point 4. With magnesium atom, I'm adding the second and the first ionization energy together to come up with 2,180 kilojoule. So the magnesium gaseous atom taking in this energy endothermically, becoming Mg2 plus ion and losing 2 valence electrons. Element 3 is chlorine. It has oxidation state of -1. The atomic radii are ranked in terms of chlorine being smaller than silicon, being smaller than magnesium. Element 1, which is silicon, has 3p2 as the last electrons, and element 3, which is chlorine, has 3p5 as the last electrons. Both of element 1 and 3 are paramagnetic because they have unpaired electron in their orbitals, which will then be attracted to the magnetic field. Let's summarize what we have learned today. The use of Coulombs Law, effective nuclear charge, and electron shielding effect to explain periodic trends of atomic radius and ionization energy. We further use the Coulombs Law to compare ionic radii of isoelectronic ion, meaning the pull between the proton, the effective nuclear charge, and the electrons. 3, the use of first ionization energy to account for increasing reactivity down the alkali metal groups. And finally, the use of successive energy, ionization energy, to identify elements. I hope that you have found this PowerPoint to be useful to you. And from the members of MLCA, we want to thank you for watching and hope to see you again next time.